Okay, guys, we're going to talk again about types of motion, but specifically we're going to focus on the third one on my screen. You guys don't necessarily need to write this down because you should already have it in your motion notes, because this was a slide I put up there when we talked about motion for the first time. We can have different types of motion. Okay, whenever we talk about an object in motion, we could talk about an object that's not in motion, so we could talk about an object at rest. We could talk about an object moving at constant velocity, and thus far we have only talked about those two, something at rest or something moving at a constant speed. Today we're going to add to that, and we're going to talk about objects undergoing acceleration. And for an object accelerating, we're looking at objects with a position that changes non-uniformly each second. And what I mean by that is if we talk about something at a constant velocity, then we're talking about something that moves from a position of like 0 to 2, 4, 6, 8, 10, 12, so on and so forth each second. Okay, so it travels 2 meters each second. If we're talking about an object that is accelerating, then instead of that regular pattern 2, 4, 6, 8, instead of that uniform change, you have a non-uniform change, where instead of a constant value that it's changing by, you might have instead positions that go from 2 to 6 to 12 or whatever. Okay, but you're going to have a non-uniform change in position each second. Okay, so that's what we're looking at when we talk about something accelerating, is positions changing non-uniformly each second. But here's your definition. Acceleration is a vector quantity that describes the rate at which velocity changes. And that's basically the equation as well. Acceleration is the change in velocity over time. That's what rate and change of velocity means. Now, this equation looks a little bit different on your AP Physics 1 formula chart, because they kind of rearranged it a little bit, but it's the same thing. Okay, it's the very first equation on this chart, whenever you look at it, is a rearranged version of this. But your acceleration is your rate of change in velocity. Now, a common misconception that students will have when we talk about this acceleration, it's a vector, and so it will have a direction, and we typically denote our directions as either positive or negative. We define our direction, we say, okay, going to the right is positive, left is negative, whatever. Okay, and students will often think that if we have a positive acceleration, that must mean the object's speeding up, and not necessarily. Okay, or if we have a positive acceleration, that object must be going forward, and again, not necessarily. It can be, but that's not what acceleration means. When I talk about positive acceleration, I'm not telling you this is moving forward. Okay, I'm not telling you this is speeding up. I am telling you that the rate of change in velocity is positive. Okay, that the change in velocity each second is a positive change. And I'll show you what I mean by that in a minute. It can mean either of those things, or both of them at the same time. Okay, but it doesn't necessarily mean that. If I say that I have positive acceleration, it could be speeding up moving forward, but not necessarily. All right, so have this definition written down. Okay, now here are 3 different examples of what acceleration could look like. We could have something that is speeding up, in which case I would say my acceleration is in the same direction as my motion. We could have something slowing down, in which case my acceleration is working opposite my motion. It's slowing me down because it's fighting against the way that I'm moving. Okay, or I could have acceleration when I change direction. So if I talk about acceleration in here, I don't just mean speeding up. I could also be talking about something that is slowing down or something that is changing direction, because when I turn, my direction changes. And so if I go from walking one direction to turning, my velocity in that direction just went to 0, because now I'm going this way. I'm not moving that way anymore. Okay, and my velocity in this direction increased whenever I turned, because when I was going this way, I wasn't going that way at all. And that's what this says. When an object turns, its motion in one direction decreases as its motion in the other increases. Okay, and so you're going a new direction. It's a vector. Your vector is changing, okay, from one direction to another. And so you're going to have acceleration occurring. All right, so back to our common misconceptions. Okay, so again, acceleration is the rate of change in velocity. This is actually another common misconception we haven't talked about yet. It is possible to have a large acceleration while moving slowly. Sometimes students will see, oh, the acceleration is this giant number. It must be moving really fast. Okay? That's not what it means. It could be. Okay? It could be moving really fast. It just depends. But acceleration being a large number or being a really small number, you can have a really tiny acceleration and be moving really fast. Okay? So the acceleration doesn't tell you how fast you're moving. Okay? That's velocity. Speeding up, this is the common misconception I mentioned a second ago. Speeding up isn't always positive acceleration, and slowing down isn't always negative acceleration. And this is a point that I believe is easier to illustrate with numbers. And so I put a data table on my screen, and if you want, it might help you to copy it down in your notes. Okay, so on my data table, I have 4 seconds of data and 5 different velocities. So I have time of 0, I have an object that's moving negative 20. Now the fact that it's moving negative 20 simply means this object is moving 20 meters per second in the negative direction. That's what the negative sign means. Okay, so to the left, if I define that as negative. And that object starts out at negative 20, but then it's negative 15, and then negative 10, and then negative 5, and then 0. Is this object speeding up or slowing down? It's slowing down, right? Because how fast are you going if you're going 0? You're not. Okay, so this object actually is slowed to a stop. So it was going in the negative direction and it stopped. Okay, so that's the first question. This object is slowing down. Is this acceleration positive or negative? What is my change in velocity each second?
+5.
Positive 5. Okay, so that's what I mean whenever I say speeding up isn't always positive. This object is slowing down and yet has positive acceleration. Okay, that's why it might be a good example to write down in case you get confused about it later. Okay, acceleration is the change in velocity, specifically the change in velocity each second. And each second, this velocity is changing positive 5. So this is positive acceleration for an object that is moving backwards and slowing down. Okay, so again, positive acceleration does not mean speeding up, and it doesn't necessarily mean you're going forward either, although it can, and we'll show you some more data in a minute. Again, in case I go too fast, y'all can open these slides on your own screen. I'm on slide 127 right now. You're welcome to head there and follow along. All right, remember, objects speed up when the acceleration is in the same direction as the object's motion. So if your acceleration and your velocity are in the same direction, you're going to get faster because they're working together. If instead of working together, they're in opposite directions, you're going to slow down. Again, in physics, positive and negative signs show direction. In fact, negative 10 meters per second and 10 meters per second are the same speed. That just means one of them's going this way and one of them's going this way. But if I asked you which is faster, you're supposed to tell me they're the same. Okay, they're just going in opposite directions. So that negative sign just means it's going the other way. So here's another set of example data. This time my object started out at 12 meters per second and then it goes 9, 6, 3, 0. Is this object speeding up or slowing down? Slowing down. It's going from 12 to 0. It's slowing down because 0 is stopped. What is my acceleration this time? Negative what? 3. Okay, so this object is moving forward, slowing down, and has a negative acceleration. That's why I said that sign doesn't tell me if I'm speeding up or slowing down, because this one was slowing down with positive acceleration, and now I'm slowing down with negative acceleration. Okay, acceleration isn't about speeding up or slowing down. I mean, that happens, but the sign isn't about that. The sign is about what is my change in velocity each second. Is that change positive or negative? All right, so again, very common misconceptions that people will miss every year, okay, on this test. So don't miss it. Put the chart in there if you need to. For me, it's a lot easier to see with numbers. All right. We can represent accelerated motion using the same tools we used for constant motion. We already talked about all of these except for the last one. We've talked about dot diagrams, which are our motion maps. We have talked about data tables. We just looked at a couple. Position versus time graphs, velocity versus time graphs, and today we're going to talk about something new called an acceleration versus time graph. In this course, we only deal with uniformly accelerated motion. That means I only deal with constant acceleration. So my acceleration isn't going to change each second. Okay, that would be way too complicated. We would need calculus for it. We're not doing that. So we're going to deal only with uniformly accelerated motion. Okay, so you'll see that later on when I go through these graphs. All right, so let's talk about what acceleration looks like on an XT graph. So just as a reminder, we've already talked about position time graphs. We've already talked about the fact that the slope of the line on our position time graph is velocity. Because acceleration is the rate of change in velocity, if I have acceleration, that means my velocity is changing. And if velocity is represented by slope, my slope will have to change whenever I have acceleration. So if you have acceleration occurring, the slope on an XT graph must change. And if you have a changing slope, it's going to be a curve like this. So if you have acceleration on an XT graph, you will see a curve. Looking at this graph, do you guys think this object is speeding up or slowing down? Speeding up is correct. How do we know that? Anybody have an answer as to why?
Exponential increase.
What's increasing specifically?
Velocity.
Okay, but how do I know that? What's velocity represented as in that graph? The slope. The slope is increasing, right? It's getting steeper. If your graph gets steeper, your object's getting faster. Okay, that means you're speeding up. If the graph slope gets steeper, like this one does, it starts out relatively horizontal and at the end it's nearly vertical. It's not quite. Okay, but that means this object is speeding up. All right, so let's look at some different scenarios. Speeding up in a positive direction. Well, that's what I just showed you. Positive direction on an XT graph still means positive slope. Okay, but my slope now has to change. If I'm speeding up, it needs to get steeper. That is an example of what a graph could look like on an XT graph for an object speeding up in the positive direction. As a reminder, acceleration and velocity must be in the same direction if you are speeding up. So whenever you look at the scenario, if it says you're speeding up, then you know that both of them either have to be positive or both of them have to be negative. Okay, so this is an example of a graph with both positive velocity and positive acceleration. And I know my acceleration is positive because I know this is moving forward, positive slope, and I know it's speeding up. And if it's speeding up, they have to have the same sign. Okay, so that's how I know the sign here. All right, let's look at the next type of graph. Oh, by the way, it doesn't have to start at the origin. This would also be an example of something speeding up in a positive direction. Okay, it still follows the same rules. It still has a positive slope that gets steeper. All right, speeding up in a negative direction. Now, if I'm in the negative direction, I need to have a negative slope. That's how I show that I'm going backwards. I'm speeding up, so it still needs to get steeper. It looks something like this. Okay, again, if I am speeding up, it means my velocity and acceleration must be in the same direction. So if I know that I'm going in the negative direction and I know I'm speeding up, then I also know that I have to have negative acceleration. Okay, in order for me to speed up, they have to have the same sign. Again, it doesn't have to start here. I could show it up here. Those are both examples of speeding up in the negative direction. Questions so far? All right, so we've looked at both examples of speeding up. Let's look at slowing down. How could you show something slowing down in the positive direction? Again, positive direction on an XT graph means positive slope. Okay, and if I want to slow down, rather than getting steeper, I need it to get flatter or less steep or more horizontal, however you want to write that. It would look something like this. An object that has a positive slope, so it's going in the positive direction, but that slope gets flatter and flatter because it slows down. Okay, again, if I am slowing down means my acceleration's working against me. If I have positive velocity, I must have negative acceleration if I'm slowing down. Okay, so this is an example of something with positive velocity and negative acceleration. Did you have a question back there, Aaron? Okay. All right, so that's slowing down in a positive direction. Okay. Okay, we got one left to look at for slowing down, and that is slowing down in a negative direction. Oops, sorry. Again, this could be anywhere on my graph. It doesn't have to be down here. It could be here. Any y-intercept. All right, slowing down in a negative direction. I need a negative slope to show my negative direction. Slowing down means I need to get less steep or flatter. This would be an example of an object that's moving in the negative direction and is slowing down. Again, if I'm slowing down, my acceleration is opposite my motion. So if I have a negative velocity here, that means I must have a positive acceleration. And again, it doesn't have to be drawn here. This would also show something slowing down in a negative direction. All right, but I said that acceleration was speeding up, slowing down, or changing direction. So let's talk now about how we can show something changing direction on an XT graph. Changing direction from positive velocity to negative velocity. If I want to show that, my slope has to change from positive to negative. Okay, because if I go from a positive velocity, that means positive slope, to a negative velocity, that means negative slope. And in order for this to happen, in order for me to change direction, I have to stop. I have to slow down, stop, and then turn around and speed up. On a graph, here's my going forward, slowing down to a stop, and here is my speeding up in the opposite direction. You're going to see a parabolic shape to your graph that looks something like this. Okay, so go from a positive slope to a negative one, and it's going to flatten out in the middle, because this is where you stop momentarily and turn around. By the way, this entire graph shows negative acceleration the whole time, because you're going from a positive velocity and you're getting less positive, you're getting to zero, and then you're going negative the whole time. So you have negative acceleration for the entire duration of that graph. Now, because I have negative acceleration and I'm moving forward here, I have positive velocity, negative acceleration, opposite sign, this part slowing down. Over here, I'm moving now in the negative direction with negative acceleration, this part speeding up. Again, if the signs are the same, you speed up. If the signs are opposite, you slow down. All right, so last one is changing from negative to positive. It looks inverted, but otherwise the same. You go from having a negative slope to having a positive one, and again, you have that moment where it has to stop and turn around so that it can speed up in the other direction. By the way, this graph has positive acceleration the entire time because you're going from a negative velocity to a positive one. So maybe it's -2, -1, 0, +2, +1, or whatever. But you're going to have a positive acceleration the entire time. Questions about XT graphs and how to represent acceleration. It's the same rules as before, it's just now we have a lot more possible scenarios that we can show.
So how do you know if it's like a positive acceleration the whole time or a negative acceleration the whole time?
Here I know that I'm moving backwards, right?
Yes.
Because I have a negative slope. And am I speeding up or slowing down for the green part? Slowing down. If I'm slowing down, I know that my acceleration has to be opposite my velocity. So if my velocity is negative, which you just told me it is, I'm moving backwards, then my acceleration here has to be positive.
Okay.
On this side, I am moving forward. And I'm moving forward and I'm speeding up. If I'm speeding up, my signs have to be the same. They're working together. So if I have a positive velocity, I must also have a positive acceleration. Or you could go back to a data table and you could say that you went from a velocity of negative, let's start with 4, to -3, to -2, to -1, to 0, to +1, +2, +3, so on and so forth. And this is my velocity values each second. What's my acceleration? What's my change each second? +1 the whole time, right? So it's +1 here, +1, +1 the whole time. Sorry?
I sort of get it.
Okay, well it's going to take some practice, but hopefully we have it a little better by the end, and if not, you'll have some time to figure it out with playlist 3, because this is part of playlist 3. Okay, so you should be able to analyze any random graph I throw at you, including this one. I've got 4 questions up here that we are going to just discuss regarding this graph, but it says, number 1 says, what is the instantaneous velocity of the object at 6 seconds? Guys, whenever I ask you for velocity on a position time graph, this isn't even just from today, just previously. How do we find velocity on a position time graph? Slope. Okay, and so if the slope is changing, that's a little trickier, but I gave you a point where it's not really. It's pretty straight right there. And so if I wanted to find my instantaneous velocity at 6 seconds, I would simply need to find the slope of the line segment that contains that point, this point right here. So I'd have to find the slope of this. So pick any 2 points along at least the straightest part that you can see. Okay, and maybe you're going to pick like this point here, I don't know. Okay, which maybe I'll call like 5.2 and 5. Okay, so that can be my point 1, 5.2, 5. And then maybe I'd pick the actual point at 6. That's at 6, 6. And so if I asked you how fast it's going, you would pick 2 points on that segment. Again, try to pick the same segment where it's moving straight. And you would do change in y over change in x. Okay, or y2 minus y1, 6 minus 5, over change in x, 6 minus 5.2. Okay, plug them in and find your slope. Okay, so that's how you could do that. Now, if I gave you and I said, hey, what is the speed, and I picked a point that's very obviously on a curve, you would have to draw in a tangent line at that point and then solve for the slope of the tangent line. Y'all know what a tangent line is from math class, yes? Some of you were telling me no. Okay. So if you had, whatever, if I asked for the slope at that point, your tangent line is a straight line that touches this curve only at one point. Like, so you can't draw it like that. Okay? Or sorry, I guess it's not right. But you definitely can't do that. Because it would cross it over here too. That's what I meant. So you would do instead, your tangent line needs to look like that. Okay? So your slope at that position. Typically you look at a tangent line as a circle. In math, but it can only touch your circle in one point. So it's kind of the same idea. You visualize like the rest of the circle for that curve. Okay, so again, find the slopes. We talked about that one. The second one, when is the object accelerating? How do I see acceleration on a position time graph? What do we say it looks like? Sorry? I'm mumbling. We're looking for a curve. Right? We need a change in our slope. So you're going to look for curve on the graph. That's when it's accelerating. So like here, we have acceleration. Down here, we have acceleration. Here, anywhere where you have a curve. When does the object have constant velocity? That's going to be anywhere where you have a straight line segment. Only, like there's one right here that I picked earlier. There's not really a whole lot of straight segments on here. A little bit here, maybe. Okay, and then the last one, when does the object have an instantaneous velocity of 0? Okay, so in order for you to have a velocity of 0, your slope has to be 0, which means you either are looking for a horizontal line segment, if you have one, which I don't, or you're looking for a point where your tangent line would be horizontal. Anytime you have something like this, where you turn around, you have to have a point right here, kind of at the peak of this, where you stop for a moment before you turn around. Like if I had picked like the point at the very top, I could have drawn in my tangent line on the board, like for like right here, like that. Okay, where it's horizontal. Okay, but if you change direction, you're going to have 0 velocity for just a split second maybe, but you're going to have 0 velocity at least temporarily. Same thing down here. Maybe at like 4.1 seconds or something. Up here, maybe at like 0.9 seconds. But you're going to have an instantaneous velocity of 0 anytime you're changing directions or if you see a horizontal line segment. So again, be able to answer questions analyzing an XT graph. All right, so we're going to talk now about velocity time graphs. We just did position time. Now we're back to velocity time. This part's a review. Again, a velocity time graph plots velocity on the y-axis and time on the x. The x-axis represents points where you have 0 velocity and the object is at rest. Anything up here is going forward. Anything down here is going backwards. Okay, again, as a reminder, you cannot determine starting position from a VT graph. So we lost a little bit of information. Our XT graph tells us a little bit more than our VT. Okay, all of that's a review. Okay, but now we have two different lines on this graph, okay, that are showing different velocity values. And so how do we interpret them? Again, on my graph here, my y-intercept tells me my initial velocity. This one started from rest, whereas this one was already moving at time of 0. Okay, so let's talk about what these VT graphs are going to look like and some of the rules. Okay, as a reminder, acceleration is rate of change in velocity. If your velocity is changing, that means your line will have a slope. Okay, for example, if you put some numbers to that, maybe this object is going from a velocity of 3 to 2 to 1 to 0. That could be true, there are no numbers, but that could be what that is showing. Okay, we only deal with constant acceleration, so we're only going to have straight lines on here with a uniform change in velocity, no curves on our graphs. So looking at this graph, is this object speeding up or slowing down? Look at my graph. Is that speeding up or slowing down?
Slowing down.
Slowing down. Because, as I said, maybe it's going from 3 to 1 to 2 to 0. Guys, how fast are we going if we're at 0? We're not. Okay, so you're going to be slowing down if you're approaching 0, which is what this graph shows. All right. So let's talk about how we can represent different types of motion on a VT graph. Speeding up in a negative direction. Okay, if I want to show an object that is speeding up in a negative direction, I need to show my line, wherever it is, needs to be in the negative region of the graph. And to speed up means that it's moving away from 0, because 0 means I'm stopped. If I'm speeding up, I need to get away from stopped. Okay, so maybe this is 0 to -1 to -2 to -3 to -4, whatever. Okay, but this is an example of speeding up in the negative direction. If you have something speeding up in the negative direction, your line will be in the negative region of the graph. Anything down here is going backwards or negative direction, and it will slope away from the x-axis. Anytime you have your line moving away from x-axis where velocity is 0, anytime it moves away from that, you're getting faster. As a reminder, slope of a VT graph is acceleration. If you didn't realize that already, okay, then you might want to write it down, but think about the equation. Acceleration is change in velocity over time. This graph, rise over run, change in velocity over time, is literally what your slope would be, is acceleration. Okay, so if you look at this, this has a negative slope, therefore this has negative acceleration. And I know my velocity is negative because I'm down here in this region. When these have the same sign, I am speeding up. So this is an example of speeding up in the negative direction. Again, it could also be here. It doesn't have to start at 0. It could be steeper. This one has a greater negative acceleration. All right, slowing down in a positive direction. Let's talk about what that will look like. If I am in the positive direction, I'm going to be plotting stuff up here in the positive region of the graph. If I'm slowing down, my line needs to approach 0, because how fast am I going if I'm going 0? I'm not. I stopped. That object is slowing down to a stop. Okay, and it's moving forward. So, if you want to show something slowing down in the positive direction, it needs to be in the positive region or above the x-axis. That's how you know you're moving forward. And if you want to show slowing down, it needs to approach 0. It doesn't have to touch it necessarily if it doesn't stop, but this one shows slowing to a stop. Again, slope is acceleration. Slope of a VT graph is acceleration. This has a negative slope, thus this represents negative acceleration. So this graph shows positive velocity, since I'm up here, negative acceleration, since my slope is negative, and because these signs are opposite, my acceleration's working against me, I'm going to be slowing down. Okay, so if the signs are opposite, we're slowing down. Again, it could be this. It doesn't have to be up there, it doesn't have to be that steep. Anything that is in the positive region and moves toward the x-axis is going to be slowing down in the positive direction. All right, what about changing direction? So changing from positive velocity to negative. If you want to show a change in direction on a VT graph, your line will cross the x-axis. That's the only way you can show it. because everything above the x-axis is forward, everything below the x-axis is backward. If you change directions, you have to cross it. This is what it looks like if you go from moving forward to moving backwards. And at this moment where it crosses the axis, where it actually intersects, at that position, that's where you're going to actually turn around. That's where you stop for an instant before you have to turn around and go the other way. Okay, so this is an example. My slope here the whole time is negative, so this whole graph is showing negative acceleration because you went from a positive velocity to a negative one, and it's uniform acceleration, so maybe it's, positive 2, positive 1, 0, negative 1, negative 2, negative 3, whatever. But you're going to have a uniform change in velocity from a positive to a negative, and that's a negative change the whole time. Again, that's if you went from positive to negative. You could also show changing directions from negative to positive, and it looks just the opposite. You're going from this region to this one. Still has to cross the x-axis. Again, crossing the x-axis is how you show you have turned around. Slope is positive, so acceleration is positive. All right, so see if you can answer this question. It says, which of the following are examples of positive acceleration? Choose all that apply. I'm going to set a timer, and I want you to turn and talk to your neighbors and see if you can figure out which of these statements, maybe it's more than one, would be examples of positive acceleration. So I'm going to give you 33 seconds, so turn and talk to your neighbor and see if you guys can figure that out, and then I'm going to ask you guys what you think whenever my timer goes off. Jack. Just checking on you, okay? All right. My timer went off, but the chime's not working. So I'm gonna, let's see, who am I gonna call on first? Is this that 6th grade? Where did I put my 7th grade one? Okay. Let's see. What did you guys say at your table, Lucas? Just tell me one of them.
Maybe I'll think.
D, object moving east and speeding up. Yeah, typically we think of east as positive, west as negative, like a number line. Okay, and if you're moving in that positive direction and speeding up, that is most certainly an example of positive acceleration. Okay, so D is a correct statement. Okay, did you guys have anything different, Emma? Anything else or just that one?
Let's see. No, I believe that should just be it, because if it was moving backwards and speeding up, that would be. Oh wait, no, it should be B2 because it's positive acceleration is slowing down. It's going to.
Okay, so yes, Emma got there eventually. It should also be answer choice B. Okay, if you have an object moving backward and slowing down, guys, if you see that word slowing down, it means your acceleration is in the opposite direction as your velocity. Your velocity is backward, it's negative. That means your acceleration is positive. Okay, they're opposites. That's why you would be slowing down. If we put numbers to it, again, it's easier to see. This is the same example I showed you earlier with that misconception, but here it is, moving backwards, slowing down. Okay, if you need to write it down again, do it. But negative 12, negative 10, negative 8, negative 6, negative 4. That's just an example. But what is my change in velocity each second? What is it? Positive 2. That's positive acceleration. So that's what the question asked. So moving backwards, slowing down is positive acceleration. Again, the negative velocities mean the object's moving backwards. Slowing down means that the velocity is getting closer to 0. Okay, but also if you see the word slowing down, you know in order for it to get closer to 0, your acceleration has to have the opposite sign of your velocity. That's how you get closer to 0. Okay, so this one has an acceleration of positive 2 meters per second every second. All right. Again, I told y'all it's a common misconception. It's easy to miss. So here is a VT graph and a couple of questions about Art and Polly. Okay, so we have these two individuals. Their velocities are plotted against time, and it says, how far does Polly travel after 5 seconds? What about Art? Polly's easier. Polly travels 1 meter per second for 5 seconds. How far do you go if you travel 1 meter per second for 5 seconds? What do you think? 5 meters. Okay, so 5 meters. Okay, what about Art? Art starts out at 0 and accelerates. His velocity is changing until he has a velocity after 5 seconds of 2.5 meters per second. If I want to figure out how far he has gone, okay, it's the same thing we did here, just as a reminder. When we did this, you did 1 times 5. You did length times width, and you found the area. You can do the same thing with a triangle, but you have to use the formula for area of a triangle. And the reason we do that is if I want to know how far Art has gone, I just have to use his average velocity. Well, the average of 0 and 2.5 is half of 2.5. Right? And half of 2.5 times 5, well, that is the equation for the area of a triangle. 1/2 base times height. That's what you're doing. Okay? 1/2 base times height is his average velocity, half of 2.5 times 5 seconds. So mathematically, finding the area is going to do that for you. Okay? And for him, that's going to be half of 2.5 times 5, or 1.25 times 5. And that will give you his displacement, okay, after 5 seconds, which is, what was that, 6.25? I can't even do math right now. 1.25 times 5. All right, yeah, 6.25. So again, find the area under the curve on your graph. I know these aren't curves, but find the area under the plotted data on your graph. That will tell you displacement if you find an area on a velocity time graph. All right, you can also answer questions about a more complicated graph like this one. For example, I could ask you, what is the acceleration of this object at time of 10 seconds? In which case you would find 10 seconds, and you see it's right here on this line. Okay, if I asked for acceleration here, acceleration on a VT graph is slope. You need to find the slope of the segment containing that line. You just pick any points on this segment, any 2 points, and do rise over run, as long as they're on this line segment. So maybe you pick this one, 8, 20, and maybe you pick the point that I just asked you about, 10, 10. Okay, and you do rise over run. Or you can pick this point and this point all the way down here. It doesn't matter. If I pick the top and the bottom of it, I have rise, -20 over run, 4. -20 over 4 is -5. So the slope of that segment is -5, and therefore the acceleration at any point on this line segment would be -5 feet per second every second, because that's the unit over here. The second one says find the displacement from 4 seconds to 16 seconds. If I look at this, 4 seconds is over here, 16 is here. Well, nothing happens between 12 and 16 because they're at rest. So I really just need to find the area of this trapezoid from 4 to 12. And so you have a rectangle here, okay, from 4 to 8. That's length 4, width 20. 4 times 20 is 80. And then you have this triangle here, base 4, height 20. 1/2 4 times 20 is 40, plus the other 80 is 120. Okay, so you'd have 120 feet in terms of the area from 4 to 12. It says 16, but again, nothing's happening here. If I asked you, when is the acceleration negative? How do I know if I have negative acceleration on a VT graph? How do I see it?
Negative slope.
Negative slope. So look for the portions with negative slope. Right here is negative slope, therefore this is negative acceleration anytime between 8 and 12 seconds. The only other part with a negative slope is right here, from 16 to 18 seconds. Those would be the portions with negative acceleration. Last question, when does the object slow down? How do I know if I'm slowing down? If I approach 0. So this part is slowing down from 8 to 12, and then the only other part where it slows down is all the way over here from 22 to 30. Okay, so those are the portions where you are slowing down. Again, be able to analyze VT graphs. The last type of graph that we're going to very quickly talk about are acceleration time graphs, and these are pretty easy because they just plot acceleration on the y against time on the x, and because we only deal with constant acceleration, all of our lines are horizontal. That's why it's easy. Okay, so the x-axis represents 0 acceleration. If I'm not accelerating, what does that mean? What might I be doing if I'm not accelerating? Moving at a constant speed or not moving at all. I've got two options. Okay, so this object could be moving at a constant speed. It could be not moving at all if it's here. Anything up here is positive acceleration. Anything down here is negative acceleration. On an AT graph, I cannot tell where I started and I can't tell how far I went. You lose information with each of these graphs. Okay, so this doesn't tell us very much at all. It just shows us the acceleration. If I wanted to show constant forward velocity on an AT graph, my acceleration would be 0 because it's constant forward velocity. Slope is 0, line is on the x-axis. What if I wanted to show something at rest? You guys just told me it's also 0. Guess what? This is the same graph that you would draw for something at rest or for something with constant backward velocity. If all I have is the graph, I have no idea if that object is moving, and if it is moving, I don't know which way it's going. I just know it's not changing its velocity. So I don't have a lot of information from just the graph, but this is what the graph looks like for constant forward, constant backward, or something at rest. All the same graph. Okay, how do I know if it's speeding up or slowing down? So if I look at this graph, and I look at this line, is this object speeding up or slowing down?
Speeding up.
I actually have no idea. Could be speeding up, but it could also be slowing down. I don't know. I just know that my acceleration is positive. That's all I know. I know the change in my velocity is positive. I don't know which way it's going. I don't know if it's speeding up or slowing down. I just know the velocity is getting more positive. That could mean it's going from -20 to -15 to -10. It could be slowing down in the negative direction, or it could be going 2, 4, 6, 8, 10. It could be speeding up in the positive direction. I don't know unless they tell me more in the question. So the graph does not tell me a lot. Okay, speeding up in a positive direction, this is what the graph would look like. That is speeding up in a positive direction. This is also how it looks on a VT. The slope of this will be this. If this slope is positive 2, this is positive 2. The slope of your VT tells you your acceleration. Again, there's the equation that shows you why that works. Conversely, the area underneath this graph, mathematically, if you rearrange this equation, you know that change in velocity is acceleration times time. So if you find this area, you can figure out how much your velocity changed, which might be useful depending on the question. But speeding up in a positive direction looks like this, but so does slowing down in a negative one. Still looks like that. Okay, because look, negative direction, slowing down, that is a positive acceleration. If this is +5, this is +5. Okay, so find the slope there. It tells you the acceleration. Again, conversely, area here tells you your change in velocity. Acceleration time graphs don't convey a lot of information. Okay, again, slowing down means acceleration and velocity are in opposite directions. They're working against each other. Negative direction means negative velocity, so if I say that you're slowing down in a negative direction, you know your acceleration has to be positive because slowing down means they're opposite. That's negative, this is positive. I know I'm going through this really quickly. Okay, y'all can go back through the slides more if you want. Okay, again, here's that same data. Slowing down in a negative direction, positive acceleration, +2. We saw these numbers earlier. So you can look at it again if you need to. All right, this is where we're going though. Okay, you're going to eventually be asked to match graphs. In fact, one of your task options in playlist 3 is to match graphs. It's called graph matching. Okay, and so you have to look at an XT graph and figure out what that would look like for VT and AT. So if I look at the first section of this graph, this object is moving forward. I know that because I have a positive slope, and that slope gets steeper. Forward speeding up looks like this. Then I have a straight line segment. Constant velocity forward. Constant velocity on a VT looks like this. Then I have it moving forward and slowing down. It gets horizontal at the end. Slowing down looks like this. That's the VT. The AT is easy. Look at the slope. This is a positive slope. Positive. This is 0 slope. 0. This is negative slope. negative. That's it. That's how your AT graph looks. You could say this object is moving forward and speeding up before moving at a constant velocity. Then as it continues forward, it slows to a stop. It's describe the motion as well. Okay, so again, be able to go from one type of representation to another. This is where our notes stop today. This is the first set of notes in playlist 3. Okay, so